there's meters, there's measuring tape on the side of this track so I can figure out the distance. So I need to stop when that is at the ground. So at 31 centimeters. All right, so I'm starting, if I start at 84 centimeters and I go to 31 centimeters, what's my displacement?
You said 31?
Yeah, I go from 84 to 31.
53.
73.
Wait.
Wait. 31 days.
84 to 31.
Oh.
53.
Yeah, 53. It's going to go 53 centimeters. In how much time? Anyone have stopwatches? Most phones have one. We're going to see how well this works. We're going to do this a couple different ways. And I said start at 84.
Yeah.
Now, when I do this, it's best to start with your sort of hand blocking it and then jerk the hand away as to holding it like this. If you hold it like this and you move your hand away, there's a good chance you're going to move it with you. So I don't want to hold it. So 84, and I want to stop when the front gets to my other finger. All right, I'm going to do 3, 2, 1, go. When I say go, I'm going to move my right hand away. 3, 2, 1, go.
93 seconds. Or 0.93 seconds.
I
All
got
right, so we got 0.93.
1.01.
1.01.
And I got 1.53.
I have 1.34.
1.08.
1.14.
I stopped mine too late.
Okay. Anyone else? All right. Now we can't just throw out ones that we don't like. Sort of. If I want to throw this one out, because that one just seems a little bit different than the others, if I throw the top one out, I have to throw the bottom one out also. Or I could just average the numbers as is. You want to toss out top and bottom, or just average the numbers as is?
Oh yeah, let's average.
Just average? All right, so someone would be kind enough to average those. Anyone else get the same thing? You at 1.17?
Yeah, same.
You round it.
1.171. She is 1717.
Oh, I got 1.178.
1.171666667.
Okay. That's what she has.
I have that.
Okay. 172. All right. It's nicer to be working in the standard units, so that's 0.53 meters over 1.172 seconds. And so what is the average velocity? Or average speed, again, because it's traveling just in one direction. Five,
5.1.
5.1. Any confirmation?
0.45221.
You have 4521.
Yeah.
Well, if you round it, yeah, that point. If you
It,
round
it, yeah, if you, it does depend upon whether you round this number and where you round it. I think we're roughly in the same ballpark. I'm shooting for precision here that it's not gonna make a difference in the end. Because
0.452.
Yeah.
you have 0.452.
Mm-hmm.
On a test or quiz, I would not notice the difference there. All right, meters per second, because it's meters per second. All right, so that's my average, and I start at 0. What's my final?
Sorry, repeat that?
If this is my average, and that's my initial value, what is my final value? What is VF final?
Oh, it's a zero because it stops moving.
What, if you're talking about when it stops moving, suddenly another force has come into play to stop it. So that, what I care about is while the acceleration is constant, so that's before it gets stopped. So how do you find average velocity besides displacement over time? There's another formula.
Force over mass.
That would be acceleration.
Minus the initial velocity divided by time.
That's acceleration.
You just multiply it by 2
Why?
because if you're gonna, it's like in final minus initial divided by 2, but since you.
Close, you're close.
Is it the other way around?
No, it's not the other way around.
The average velocity is the final velocity minus the initial
No.
velocity, or wait,
All three of you
maybe
made the
sorry.
same mistake in the numerator. And I see this on tests too. How do you average numbers?
You divide it by however numbers, how many numbers there are.
What do you
You
divide
add-
by however many numbers?
Is that, you add them, not
So-
divide them. Or you add them, not subtract them.
Yeah, it's the initial velocity plus the final velocity divided by 2. So close. Now, in this case, my initial velocity is 0, so you're gonna get the same answer either way. But if the initial velocity is not 0, you would definitely not get the same answer. All right, so so the average of this and this has to be that. So in this case, it's just gonna be twice that. So my final velocity is 0.904 meters per second. Because 0 plus VF divided by 2 is 0.452. This is the math way. Multiply both sides by 2, and then subtract your initial. So, what was the acceleration? If I have my initial velocity and my final velocity, I know how much time it took. How do I find acceleration?
Change the velocity divided by, isn't the change in velocity divided by the time?
Yes. And so what's my change? So acceleration. Change in velocity over time. What's my change in velocity?
The 0.904.
Yep. Technically minus 0, but yeah, they get you there. 0.904 meters per second. Divided by the time, 1.172. And so what do we get as the acceleration?
0.771
0.771.
meters per second squared.
Thank you for answering before I asked that question. All right. How accurate do you think that is? And that probably, I see a couple people doing this. Yeah, I probably agree with that one. Let's find out. Let's figure out what the prediction is, and then we'll find the acceleration a different way. So I'm plugging into F equals ma. I'm trying to find acceleration using this formula right here. We are assuming that this formula is true, regardless of what we actually get right now. What is the mass involved here?
The weight of the thingy. The
Ooh,
gun.
oh.
The mass of the
The mass
cart.
of those buggy thingy.
Okay.
Now I need more detail. The mass of what?
The cart. Or like, isn't that
The
the,
weight, the
500 grams and 50 grams.
weight hanging.
Why both of them?
Because both of them involved, like this one, no. Like
Because
that
they're-
one pushes down and that one moves, so.
Yeah, because they're connected and both being pulled by the same force.
They have the same acceleration. They are moving together. So it is the total mass that's being moved here. I don't want to get rid of, I guess I have that down there. So the total mass that's being moved here is the sum of the two. So I got 510.74 and 50.4, it was 50.40. But we didn't need that level of precision anyway. Carry the 116. Did I make it Carol, Sarah?
nope, that's right.
All right, that is grams. So how many kilograms is it? Oh.
0.5614 kilograms
Sorry, where did you put the decimal point?
in front of the 5.
All right, so that's the total mass that's being moved. It is not the weight. Or maybe I just misheard. Now we have to figure out what is the force. This is the driving force. This is the force that is causing the whole thing to accelerate. So what force is causing the whole thing to accelerate?
Gravity acting on the hanger.
Yes. Let me nitpick that. What is the force?
Gravitational pull.
Yeah, I'll buy that. You just said gravity.
Oh. But I think we're gonna pull it back to tension on the rope.
No, if you want to get into the nuts and bolts of it, technically, it's the force of gravity pulling that down and the tension keeping it from falling. It's the tension pulling on this. Mathematically, you get two equations, two unknown, tensions cancel out. I can show you in more detail later. I can show anyone in more detail later. Just not everyone's into solving simultaneous equations. All right, we got a handle on that equation right there. So the force is the weight or the gravitational pull on the hanger. Well, I know what the mass is. The mass of the hanger is 0.0504 kilograms. How do I find the weight?
mg.
So 0.0504 kilograms times,
9.8.
we can do better than that,
7 something.
1.78.
798. Now, there's probably so many errors involved here that this is not good, 9.8 would get you just as well, but it seems like when you're doing a real experiment, you should use the real number. And so what is the weight of the hanging mass?
Oh, 0.4988. Six.
You got 0.4938? We got confirmation over there?
Yeah, I got the same.
9.8.
You still taking this?
Oh, I see what it is. Yeah, I typed in wrong.
All right,
Yeah, that's it.
did you say units?
Newtons for it.
Yeah. If you wrote down kilogram meters per second squared, that's also true. So we now know what the force is, we know what the total mass is, we should be able to predict the acceleration. We have 0.5, the wrong one, 0.4938 equals 0.56114 times the acceleration. This is F, it's equal to ma. So the acceleration should be 0.4938 divided by 0.56114. And we're getting closer than I actually expected us to. I think we ate something.
0.88 if you're rounding.
0.88.
0.880028.
I'm good with 88 then. It's not math class, need units.
Meters per second squared.
And we 0.77. It's only about 14% off. Probably one of the best in-class demos I've done on something like this. Let's see if we can get better. So apparently, that, too bad I erased it. I'm wondering if we got better results if we got rid of the top and bottom. All right. Questions up to here before we find acceleration a different way.
Wait,
Yeah,
so
go ahead, Lynn.
how we did the first time, is it involved with our times that we got all different ones? Like the times where we pushed through stuff?
Yeah, we use those times to figure out the average velocity, which gave us the final velocity, which gave us the change in velocity, which gave us the acceleration.
Yeah, and that would, a more accurate thing of that would equal more of this answer, right? The
I hope.
0.88.
Yeah, well, we'll find out if there are better ways of doing it than reflexes. Now, in a lab, you generally don't have, we had what, six different results
Yeah.
there. So that should be slightly better than, you got one person or two people doing it. However, let's go back to, I guess, something we touched on earlier. Let's see, I want to save some of this stuff, so total mass is 0.56114 kilograms. And the weight of the hanging mass is 0.4938 meters. Oh, and our predicted acceleration. .88 meters per second squared. All right, as this thing was moving along, its acceleration, we're assuming is constant. As long as the force on the mass hanger was staying constant and there's no additional forces getting thrown in, force should have been constant. So my acceleration, first time graph, that's 0. It was something constant. So if my acceleration is constant, what should the velocity time graph look like?
Speed up.
Slope is constant. So working backwards, I know the slope of this is the acceleration. The slope is constant and positive, acceleration constant and positive. What will displacement first time look like? Not if I understood your hand gesture correctly. Dulce, you were doing
I think it'll go in the same direction as the velocity slope.
like that, which I think is what you were doing. It's gotta be, the trouble with that, if I got displacement in time, if that's straight line right there, what would the velocity graph look like?
Oh, wow.
It'd be constant, so it would be covering more distance in less time, so it would look like half a great U shape.
Yeah, so it'd go like that, right?
Okay.
Well, I didn't realize.
Yeah, alright, so I know my slope starts out small and increases, so as was said here and his hand gestured over there, it was like that. You said half of a U shape, it's part of a parabola, for those who recall that word parabola, part of a parabola. Recap. Who's dealt with parabolas before? So, it's like about 5 2/2. Do you happen to remember what the formula for parabola is? Generic formula?
Like the quadratic equation?
Sorry?
The quadratic equation?
Yeah. It's a quadratic equation.
AX squared plus Y equals AX squared plus BX plus C.
Yeah, that's the generic equation where A, B, and C are just some number. If A is positive, the parabola goes like this. If A is negative, it goes like that. The LabQuest will give you this form right here. If we can somehow measure the position of this with the LabQuest, we can just do, there's a thing on the LabQuest that does curve fitting. So we pull out the motion sensor that I'm sure all of you know and love. Pull out LabQuest 3 and hope that it has some juice in it. Well, it's got something in it. And unfortunately, I don't have a document camera, so there's gonna have to be, sort of the classic show and tell.